So we left off on Monday. We'd started talking about organizing data graphically. And we'd hit on a couple of different constructs. One was a table, and what we used was called a frequency table. And when we were doing categorical data, we listed out all the categories. We looked at favorite color. And we just had red, blue, and green. And I don't remember what the numbers were that we had, so I'm just going to throw some numbers in here for us. Let's do 14, 16, and 20. Can't help you out right now. You want to take a test? It's right there. So let's say those are our frequencies. If we want to graph those. We did a bar graph was one of the things we did. And we discussed, what we had discussed was called a vertical bar graph. And that vertical bar graph, we had the categories along the bottom, red, blue, and green. It might be a little deceiving if we were talking about valid statistical displays. I would discuss how it might be inappropriate for me to use one of the colors named to construct the graph just because there is a psychological effect there. But anyway, we labeled all the way up to our largest number, which is the 20, and then we put in the bars. Red goes up to 14. Blue goes up to 16. And green goes up to 20. We discussed the strengths of these, how if we want an exact number, you're best to go to the table. Because even here with the green, is that 20 or 19 or 21? It's not easy to tell for sure exactly what value it is. The table, we can look at there and we say, yeah, green is exactly 20. The graph, its strengths were finding the largest and smallest. And then comparing. If I asked which was chosen more, red or blue, we can look at it very quickly and see, hey, blue is taller than red, so blue was chosen more than red. Other graphical displays we might have for this. On the bar graph, we could have a horizontal bar graph where we put our red, blue, and green on the side like this, and our scale would go across the bottom. So we'd have 5, 10, 15, 20. And our bars would go that way. So we've got 14 for red, 16 for blue, and 20 for green. Either one is an acceptable display for categorical data. We can either be vertical or horizontal. When we get into numerical data, we'd have to use a vertical bar graph. And we'll discuss that in just a minute. Now, a third type of graph for categorical data is called a pie graph or circle graph. Now, technically, if we're looking at categorical data, it's called a pie graph. If we're looking at numerical data, then it's called a circle graph. The process for creating it is the same either way. Normally when we're looking at a circle graph or a pie graph, what we are going to be graphing is the percent, the relative frequency. So that relative frequency number is found. We first must find the total. So we add those all up. That looks like that adds up to 40. So the relative frequency is found by dividing each number by the total. So 14 divided by 40 is 0.35. 16 divided by 40 is 0.40. And 20 divided by 40 is 0.5. So to make that circle graph, rather than, like I said, at one point we would go through and we would actually figure out how many degrees out of 360 0.5 is and whatever. For our purposes, we're just going to look at 0.5 as 50%, changing it to a percent. 0.4 is 40%, and 0.35 is 35%. And we're going to graph those percents. So on a circle, half of a circle is 50%. Quarter of a circle is 25%. If I cut a quarter in half to make an eighth of a circle, that's about 12.5%. And using those, I can get a pretty good approximation of the graph for most sets of data. Now here we have the green, which is exactly 50%. So I just go ahead and cut this across there. That's my green right there. Of course, I can get rid of the labels. For blue is 40%. While looking at this, that doesn't add up, does it? That doesn't add up to 40, that's why. How about I change this? Nobody caught me on that. Those numbers don't add up to 40, do they? They add up to 50. That changes things. So when we divide by 50, 14 divided by 50 is 0.28. 16 divided by 50 is 0.32, and 20 divided by 50 is 0.40. So that'll change this quite a bit. But going back down here, red is 28% then. That's just bigger than a quarter. So that's going to be red. The green is 40%. Well, if I think about that, this is a quarter is 25. This is 12.5. 25 and 12.5 would make 37.5 total here. So 40% is going to be slightly bigger than that. So probably somewhere in there. So that is going to be my green. So the rest of this will have to be blue. I mean, we don't need to be any more exact than that because most of you are pretty good with computer programs. If you're familiar with Excel, you know that you can put that into Excel and pop out that graph really quickly without having to measure out the degrees and everything like that. So that's really as precise as we're going to get in here, is just using those approximations to graph it out. If we're looking at then on the categorical side of things, and we've already talked in this last unit about bar graphs, or sorry, the numerical side of things. We've already talked in the last unit about bar graphs and even the line graphs for time series data. So rather than discussing any more about that, I want to move on, and if we have extra time before the end of this unit, I might come back and discuss a little bit more about frequency tables and stuff for numerical data. But I want to move on now to the next step, which is talking about summarizing data numerically. Now, most of these summaries that we're going to be looking at calculating, you guys have probably calculated before. So my main emphasis today, I want to look at what do they really mean? What do they come from? Well, what it all comes from is something called a data distribution. And probably the most intuitive way to display a distribution is on a number line. So let's say we're looking at test scores from the last test. And let's say those scores the lowest score is 80. Let's say the highest score is a 95. So those test scores are distributed from 80 to 95. So let's say I grade the first test and the score is an 87. So I'm just going to put a dot above the 87. So this would be called a dot plot. I'm just plotting dots on the number line above the values for the data points. I grade another test, I get a 91, so I'm going to put a dot at 91. The next test, 84, so I put a dot there. Next test, 88, so I put a dot there. Next test, 94, so I put one there. Next one, another 88. A 90, let's say there's an 89, 82, 86, another 87, a 90, another 88. And you can see as I score these tests and I plot them on here, this starts to take shape and it starts to form a definite pattern or distribution. And now with a small number of tests, you usually don't get a great distribution. But if you have enough values, enough data points, you can get a pretty clear picture of the data. And even here, you're starting to get a picture of what this curve would look like. Tracing out at the top of those points, or those dots, I get a curve like that. Many of you have probably heard of something called the bell curve. If you talk about curving grades on a test, this is what they're talking about, is using a bell curve. The technical definition, the statistical name for this is something called the normal curve. And it's called the normal curve because most things in nature actually follow a distribution like that. That is the distribution that items normally take. The height of people forms a bell curve like that. Scores on a good test forms a bell curve like that. The hourly wage of people in a certain industry will form a bell curve. All sorts of numbers in nature or naturally occurring will form that normal distribution like that. So when I look at that bell curve, I'm going to redraw another one down here. It's a little bit less cluttered. Take the dots out of it. So I'm going to start out with this red bell curve again. So there's my curve. One of the things I would describe about this curve is its center. This is the center of the curve. That looks to be about 88. So if I was describing this curve, I would say the center of it is at 88. Well, I might have another curve that's the same shape as it, but it might be right here. So if I were describing the difference between the red curve and the green curve, I'd say they're the same shape, but the red curve has a center at 88, the green curve has a center at about 92. So they have a different center. So that's one of the things we're going to describe about this curve is its center. Next, I'm going to draw another curve here. Comparing the purple curve to the red curve, well, they both have the same center. Their center for both of them is right around 88. The difference between the red curve and the purple curve is the purple curve is narrower, or you could say the red curve is wider. That trait is what we call spread. Sometimes they use a fancy term, dispersion. The purple curve is less spread out than the red curve, or the red curve is more spread out than the purple curve. There are several ways numerically to describe the center and spread. So what we're going to start out with here is describing that center. So to describe center, There are, well, several different measurements of center. We're going to discuss 4 of them. The first one we're going to discuss is the mean. The mean is what most of us have called the average. From somewhere around 3rd or 4th grade, we started calculating averages. You add the numbers together and you divide by how many are there. So what we're going to do is we're going to define something called n here. N is the number of items or of numbers in a set. So the definition here for the mean is you add up all the numbers. So the notation there, that symbol means sum of xi just means each of the individual numbers. Then you're going to divide by n. You're going to divide by how many are there. So I'm going to come over here and I'm actually going to create a set of numbers that we're going to use here. So I'm going to use the set of numbers. Let's do 7, 13, 25, 15, 21, 14, let's see, 1, 2, 3, 4, 5, 6. I'm going to go one more number here. I'm going to put in a 10. So to find the mean of those numbers, I'm going to add them up. So 7 plus 13 is 20, plus 25 is 45, plus 15 is 60, plus 21 is 81, plus 14 is 95, plus 10 is 105. So they add up to 105, and I have to divide by n. Well, n is going to be 1, 2, 3, 4, 5, 6, 7 numbers. So I'm dividing by 7. 105 divided by 7 is 15. So the mean of this set of numbers over here is 15. That's one measure of center. Another measure of center, the second one we're going to look at, is the median. The median is the middle number. So to define the median, there's actually a couple of things we have to do. The first thing we have to do to find the median is to put them in order. So we put our numbers in order from smallest to largest. So going over here, smallest is 7. Next looks like 10, 13, 14 first, then 15, 21, and 25. Just to count them 1, 2, 3, 4, 5, 6, 7. There's 7 of them there. I'm actually going to number them 1 through 7 just because that's going to make the next step a little bit easier. So back over here, our second step is to find the position of the median. So the position of that median, the median is going to be halfway through the data. In fact, the technical definition of the median, the definition of middle, is half of the numbers are on each side of it. So the position is going to be n times 1/2, or n times 0.5. So for this set of data, n is 7. So 7 times 1/2 is 3.5. So since we got a decimal there, a decimal or a fraction, what we have to do to find the position of the median is take that number and round up. So what that means is the 4th number in our list is the median. So the 4th number there is 14. So our median here is 14. Now I see the mean was 15, the median is 14, so there's a small difference between them. Now, in this case, n was odd. And when n is odd, we do get a decimal for that location, and we round up. What if n was even? So I'm going to actually create a second set of numbers over here. And I'm going to put them in order as I create them just to make it easier on us. So 9, 13, 15, 15, 17, 20, what's that? 1, 2, 3, 4, 5, 6, 24, and 30. So there's a set. This set now has n equals 8. 1, 2, 3, 4, 5, 6, 7, 8. So if I'm finding the median in that set, I find that position again. Now n is 8, so it's 8 times 1/2. Oops, 1/2, which gives me 4. Since this is a whole number and not a decimal, that tells me that my median is between that and the next number. So it gave me 4, so it's between the 4th and the 5th numbers. So over here, fourth number is 15, 5th number is 17. So my median is between 15 and 17. So to do that, I average those together. 15 plus 17 divided by 2 is 16. So the median of that second set of numbers would have been 16. The reason the mean and the median are discussed first is those are actually the two most important measures of center. Considered to be the two most significant as far as statistical processes. And we'll come back to that in just a second. Let's talk about a third measure of center, which is the mode. The mode is the number that occurs most often. Now looking at my sets of data over here, the top set, there is no mode. There's no number in that first set of numbers that's repeated more than once. Now in the second set, there is a number, the 15 is repeated twice. So the 15 is the mode. Now for numerical numbers, we tend to not use the mode. The mode tends to be used most for categorical data. So for numerical data or quantitative data, the mode isn't such a big deal. But when we're dealing with categorical data, we don't have numbers really to average together to find a mean or to put in order to find a median. We're looking at categories. So the mode is the category that is selected the most often with the highest frequency. So the mode is really only useful in categorical data. Another measure of center is something called the mid-range. The mid-range is pretty simple. It's very quick, and for a good set of data, it'll be relatively accurate. The mid-range is found by taking the minimum, which is the smallest number, and averaging it with the maximum, which is the largest number. So it's the minimum plus the maximum divided by 2. So back to our original set of data up here. We're going to use the ones that are in order for our median. We've got 7 plus 25 divided by 2. Well, 7 plus 25 is 32. Divided by 2 gives us 16. So we've got a mid-range of 16. So now let's compare. We're going to look for that top set of data there. We had a mean for that top set of data, what was it? A 15. We had a median of 14. We had a mode that didn't exist. And we had a mid-range of 16. So those numbers were close, but not exactly the same. Now we're going to exclude the mid-range because that's kind of a lesser used one. We're going to talk about the mean, median, and mode for a second and what it means for them. In a normally distributed set of data, if it was perfectly normal, so perfectly normally distributed, the mean would equal the median, which would equal the mode. They would all be the same. Some symbols, by the way, the mean, if we're dealing with a population, the symbol for mean is the Greek letter mu. If we're dealing with a sample, we use X bar for the mean. The median, depending on what we're looking for, is usually a capital M. Mode, we don't really have a symbol that we use for it. But for the mean, that mu symbol, against the Greek letter mu, and that X bar are very important. X bar is for a sample, mu is for a population. So if that was a true bell curve, just looking at the bell curve, it's pretty easy to pick out the mode. The mode is the tallest point of the bell curve. That's the number that occurs the most often. It's the highest point. That'd be the mode. If this were truly normally distributed, that same point would be the median and the mean. Now, if they're not the same, what does it mean? Well, this, like I said, is perfectly normally distributed. Perfectly normally distributed, it's symmetrical. I could cut this down the middle, and it would one half would fold over onto the other half. If it's not symmetrical, it's considered skewed. So if it looks like this, I'll make it a little smaller, I'll put these side by side. That is called skewed left. Think of it, the left end of it's been stretched out. If it looks like this, that's called skewed right. It looks like the right end of that has been stretched out. Well, when it is skewed left, the mode is still the tallest point here. That's still the mode. The median will move slightly towards the skew. That's the median. And the mean is going to move the furthest. Depending on how far stretched out that is, that mean is going to move over more. Of course, it'll be just the opposite over here. I'm just going to color code them. The median is purple. That's the highest point. The mode is purple. That's the highest point. The median moves a little bit off towards the tail that's skewed. And the mean moves a lot more. So if you're asked which one is a better measure of center, the mean or the median, most people would select the mean. And just some psychology behind it really is they've been using the mean for a lot of years, calculating the average. And also, it seems very satisfying. We have that formula. You add the numbers together, you divide by n. But in practice, the median is affected less by the skew. The median stays closer to that large number, or that most often number, the mode. Why is that important? Well, let me give you an example. In 1983, I believe it's 1983. I'm not sure if it's 1983 or 1984 for not right now, but we're going to go with 1983. The University of Virginia advertised that the average starting salary for a marketing graduate from their school. Now, marketing is a pretty generic degree. It could be dealing with sales, could be dealing with advertising. Pretty common business degree. They're saying the average starting salary for a marketing graduate with a bachelor's degree was right around $78,000 per year. Now, $78,000 is a pretty impressive starting salary now. Go back to 1983. In 1983, your average high school teacher was starting out of college, their first job, $17,000, $18,000, if that. Some of them down to $16,000 a year. So $78,000 was an impressive starting salary. But what they did not disclose was that one of the graduates that year, and actually did graduate with their degree in marketing, was a young man by the name of Ralph Sampson. Mr. Sampson was 7 foot 4 inches tall and had been the two-time NCAA basketball player of the year. Was drafted number 1 by the Houston Rockets. Now, as you can guess, he might have made a little bit more than $78,000 that year. He had a multi-million-dollar contract. Well, it takes a lot of $20,000 marketing graduates to average out that multi-million-dollar contract to $78,000. In fact, Mr. Sampson was the only one in that group of graduates to make more than $33,000 that year. This was obviously a mean here. So his one really, really large salary really changed the number. The median was between $23,000 and $24,000. Quite a bit different from $78,000. So the median is considered to be, like I said, more stable. It's not affected by outliers as much as the mean is. The next thing we want to talk about is we want to talk about then those measures of spread or dispersion. And there's only a couple of them we're going to discuss. The first one we're going to discuss is something called the range. The range, related to our mid-range, is just the largest number, which is the maximum, minus the smallest number, which is the minimum. So for our top set of data up here, that largest number was 25, the smallest number was 7, giving us a range of 18. That range, however, is not really good at distinguishing between sets. Precision was a term we threw out there. If I put two sets up here, let's say let's do a 12, 15, 16, 17, and 24. Is that going to work? Actually, no, that's not going to work. I'll make this 8 instead of 12 here. We'll do 8, 15, 16, 17, and 24. Then we're going to do a second set. 8, 9, 16, 23, and 24. Now you might agree that those are not equally spread out. If I were to do a dot plot of those numbers, now I'm just going to do this over under 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. The top set of numbers I'm going to do in blue on top. It's 8, 15, 16, 17, 24. Well, those are mostly concentrated in the middle. If I do the bottom set in red below, I've got 8, 9, 16, 23, and 24. Those look to be much more spread out. But for either one of them, if I find the range, either one of those sets have a range of 24, the largest number, minus 8, the smallest number, giving me a range of 16. So we need a better way of distinguishing, of describing that spread. So what we're going to do is we're going to do something called the standard deviation. So the standard deviation actually is a 6-step process, and each step has a name. So let's walk through that process. Step 1 is going to be to find the mean. So we're going to do the top data set here. So 8 plus 15 is 23, plus 16 is 39, plus 17 is 56, plus 24 is 80, divided by 5. N equals 5 here because there are 5 numbers in the list. So that gives me a mean of 80 divided by 5 is 16. My second step, we're going to subtract the mean from each number. These results here that we're going to get are going to be called the deviations. So I'm actually going to list out those numbers, 8, 15, I'm going to go jump down here. 8, 15, 16, 17, and 24. And I'm going to subtract that mean of 16 from each. So 8 minus 16 is negative 8. 15 minus 16 is a negative 1. 16 minus 16 is 0. 17 minus 16 is positive 1. 24 minus 16 is a positive 8. As I said, these are called the deviations. Step 3 is to square the deviations. And you probably guessed the name is going to be the squared deviations. So negative 8 squared is 64. Remember, anytime you square a number, the result will be positive. So be careful when you put it in the calculator. You have to put parentheses around negative when you square it. Negative 1 squared is positive 1. 0 squared is 0. 1 squared is 1. And 8 squared is 64. Again, these are the square deviations. Step 4 is to find the sum. The sum, you just add those up. 64 plus 1 plus 0 plus 1 plus 64 is 130. That would be called the sum of the squared deviations. Step 5. Divide by n minus 1. This is if it's a sample. If it's a population, you would divide by n. But we're assuming this is a sample since it's only 5 numbers. We're going to divide by n minus 1. So n equals 5 here. So n minus 1 equals 4. 5 minus 1 would be 4. So we're going to take that previous result, the 130, divided by 4, which gives us 32.5. That number right there is referred to as the variance. And finally, we get to our last step. Step 6, square root. So we're going to do the square root of 32.5, which is going to give us 5.70. That number right there is finally the standard deviation. What that is telling us is on average, each of these numbers is 5.7 away from the mean. Let's do that second set just to compare. Well, that second set, the mean, I'm just going to give you the mean is also 16. I did that intentionally. Step 2, we're going to subtract the mean from each. So we've got 8, 9, 16, 23, and 24. And we're going to subtract the mean. So 8 minus 16 is negative 8. 9 minus 16 is negative 7. 16 minus 16 is 0. 23 minus 16 is a positive 7. 24 minus 16 is 8. Step 3, you square them. Negative 8 squared is 64. Negative 7 squared is 49. 0 squared is 0. 7 squared is 49. 8 squared is 64. So there's our squared deviations. Step 4 is to find the sum of the squared deviations. So I add those up. I get 226, I believe. So there's my sum of the squared deviations. Step 5 is to divide by n minus 1. So I'm going to divide this by 4 since n is still 5. That is, what, 56.5, is it? So that is the variance. And I square root that to find my standard deviation. That's step 6. Square root of 56.5 is 7.52. That is my standard deviation. So this bottom list had a standard deviation of 7.52. That top list had a standard deviation of 5.70. So you can see that top list, the standard deviation does tell us that that is much less spread out than the bottom list of numbers is. Okay, that's about it for today. We will go over another example of the standard deviation probably on Friday. And then we'll talk more about what do the standard deviation and mean actually mean. What do they represent in a set of numbers? It's a very significant meaning there. But for now, in the book, there's page 321, 1 through 7, the odd, dealing with some of the graphs. Page 326 through 330, and we've already done some of the graphs in the last unit. 1 through 10 is dealing with some of the vocabulary and the charts a little bit more. And finally, page 339, 340, 1 through 9, the odds, looking more at organizing the data. And I want to take just a little peek at page 347 and 348. 1 through 9, the odds, is talking about the mean, median, and mode. Like I said, on Friday, we'll talk a little bit more about standard deviation, and then we'll look at what does the standard deviation and mean represent when we apply them to a set of numbers. So you guys have a great day. We'll see you on Friday.